Works Journal, and he also serves as the general co-chair of Mobicom in 2012, and he also the TPC co-chair of Infocom in 2017, and he is an IEEE fellow. So let's welcome Dr. Ekici.
Thank you very much for the introduction. Can everyone hear me? Okay.
Yeah.
All right. So let me see if I can actually share the correct thing with you all. Is this good?
Yes.
All right, perfect. So, before we even get started, there's a chance that I may have to take about 30 seconds or so of a break in case somebody gives me a call to fix our heating system. So I hope everybody appreciates the fact that it may be very important over the weekend to have heating at home, which I currently do not have. So, so there may be a brief introduction, interruption to my presentation. Hopefully, you will excuse me for that if that happens. So today, what I'm going to talk about is a brief overview of our work on joint radar communication systems, specifically targeting vehicle-to-everything systems, but also which is also expandable to other communication platforms and environments as well. So let us start with how this came to be. So this work actually dates back quite a bit. I would say almost, I mean, its initial steps were taken almost 8 to 10 years ago. And the idea there was that we anticipated a spectrum crunch for vehicle-to-everything systems. At that time, we had about 70 megahertz of bandwidth, but the applications were becoming more and more bandwidth hungry. And so we were exploring different venues to include more spectrum into our communication system. And well, although a little bit with a little bit of delay, we saw that spectrum even shrinking to 30 megahertz, while potential for more bandwidth demand was increasing. So with that, we also identified the automotive radar systems, which have been allocated the 76 to 81 gigahertz spectrum, which were quite a bit of underused. And therefore, we wanted to utilize this spectrum to both use them for sensing as well as for communication. And that was the basic idea that we started out from. So here, for example, the one vehicle that is, hopefully you can see my pointer here, would be able to use the same spectrum for both sensing as well as for communication at the same time. So we started asking ourselves, is it even feasible? So if we were to push communication into that spectrum, are we giving up something on the communication end? So we assumed that we were utilizing a full spectrum that is given in a band for radar sensing. But then we were also trying to figure out what would happen if we were to also add communication to that. So what we did was we looked at this from a theoretical perspective, and we said, well, there is individual sensing devices, for example, here. They get the information individually and they keep it locally. On the other end, let's say we also have the same system. Now we are allowing these vehicles to communicate with each other, to exchange the sensing information among themselves and improve their sensing quality through shared information. So this way, rather than spending this whole time for sensing, they would just spend a little bit of time sensing and then exchange the information and hopefully get the same to the same level of sensing quality. So this win-win collaboration would allow us to communicate and sense a little bit less of a time, and whatever leftover periods are there, we would use them for communication. So with sparing you most of these details, what we have looked at was the Kramer-Rao lower bound of the accuracy. So the lower this Kramer-Rao lower bound is, the better we are off. Alpha here represents our correlation between different sensing procedures. And we have been able to identify that there is a sweet spot whereby you dedicate a certain fraction of the time to radar imaging, and then the rest of the time to for communication. And it turns out that at about 40% of the time, if you were to sense 40% of the time in the numerical scenarios that we have run, the remaining time can be dedicated for communication, for arbitrary communication, and while we are still maintaining the same level of efficacy for radar sensing. So what this told us was, even though we may want to assume that we need the full time for radar sensing, if we do collaborative sensing, we can actually carve out some time for communication. On the other hand, if we just leave everything else out and assume, observe that the radar band is underutilized, there's already plenty of time for communication anyways. So this gave us the green light for us to move forward. So with this theoretical backing in our pocket, we started implementing two different scenarios through which we would do joint radar processing and communication. In the first case, we just looked at an OFDM system that uses pilots already regularly, and we wanted to use the pilots symbols for sensing and the rest of the functionality for communication. Now, with the pilot signals, we would do both channel estimation as well as radar functionality. And then the rest of the time, and with the rest of the resources, we would do the communication with the objects that we want to communicate with. So here we are doing both high accuracy distance estimation as well as velocity estimation. And we are implementing on the same platform the communication functionality as well. So here again, the reflected pilots are received, then they are processed to estimate the radar parameters, and all the blue periods and resources that you see here is used for communication. So I'm going over the details a little bit fast here, because what we wanted to show here is that we can actually get a lot of information out of the system, such as range and Doppler, which would be translated to speed. But here, this angle estimation is left out because we don't have, in this case, the capability of sensing the directionality, which we'll be taking care of later. We went ahead for the with a proof of concept implementation with commercially available USRP platforms, front ends, and a host PC that does all the implementation. And we, in fact, implemented this at 78 gigahertz. So this dates back to 2019. So this is the platform that we have developed. So there are two identical systems with USRPs and a front end and horn antennas for transmission and reception. The range resolution was 1.5 meters. The velocity resolution was 4.7 meters, and the maximum bitrate was at 60 megabits per second with QPSK, but it was significantly limited due to the baseband processing that was done at the computer, at the host computer. So here is a little demonstration video that we have. Again, these are the components that we are using. We are using this 76 to 78 gigahertz oscillator. So this is the test bench that we have used with the communication transmitter and the receiver. And this is what you observe at the transmitter interface. We have the radar map as well as the video display. So on the right hand side, you see the constellation of the received symbols, and here you see the live video while we are actually also doing getting the radar signals back. So I believe we had this. Let me excuse me for 1 second. Why this was. So this became to an end here. Okay. So in this case, we had we move on to the next step of our work, where we now include a MIMO front end to the OFDM system. And this is for short range and medium range radar operations. Now, what we are doing here is that we have both multiple signal transmission and receive chains for high resolution imaging, as well as adaptive precoder design for simultaneous multi-user communication and MIMO radar imaging. The way we accomplish this is by using two stages of radar sensing. One of them is using non-data packets for estimation of the reflectors and the targets. And the second part is using pre-coded data stream to refine the resolution, as well as to communicate our data to the objects that we want to communicate with. Here, I just want to highlight the fact that we can do only radar sensing, only communication, or joint radar sensing and communication with select users all in parallel. So one of the features that we are using here is that we can create this virtual ULAs, whereby we have a certain number of transmit antennas spaced at a critical spacing, and the receivers that are placed at a number of transmit antennas times the critical spacing, so that, for example, if you have 4 transmitters and 2 receivers, you have a virtual NTX times NRX, in this case, 8 receiver antennas, which actually increases our resolution quite a bit on the radar side. So for the OFDM, MIMO OFDM waveform, we have the orthogonal preamble, which does the full transmit diversity for channel sounding, and with the pre-coded symbols, spatial multiplexing for improved joint performance is achieved. So again, these steps include a non-data packet transmission period for general sensing of the environment, and then the pre-coded transmission based on the estimated CSI obtained from the first stage to fine-tune the measurements to improve the communication and radar SINR performance. So what is to be gained out of this? If you were to just go with the non-data packets, this is the map that you would get for range, and then as well as the directionality. And then if you then add the pre-coded transmission with SINR threshold for communication, then you can also form the following beams as are shown here in white. And then you can improve the contrast between the background and the received signals from the targets significantly. And what you can see here is that with this resolution, you have a much higher performance on the radar end. And here you see, for example, the communication target and the radar target is co-located. 2 other targets that you want to just sense, and then another communication target that is not sensed. So you can adjust your beamformers accordingly, and also suppress a lot of the background noise at the same time. Moreover, we implemented this also on a custom MIMO OFDM testbed. For this one, we have used, again, USRPs with a local oscillator sharing here. And then we created a custom front end for the system. This is on the transmitter side. And on the receiver side, we have used a much simpler receiver just to show that we have the capability of receiving data. And this is now operating at 24 gigahertz. And the main reason for that is basically cost, because if you were to go all the way up to 78 gigahertz, the cost of the components and the availability of the components were really becoming prohibitive. So those components that we could find out in the marketplace, they were a lot more expensive, and the lead time were measured in 6 to 12 months, and that was at the height of the pandemic. So it was pretty prohibitive for us. So let us see some of these performance videos here. So here on the left-hand side, you see the video of the target moving. Here's a reflector that my PhD student who has now graduated is holding. And here you see the radar image with the angle and range measurements. And the estimation of the range is given here on the right-hand side, as well as the angle estimation that is changing over time. And the signal to noise ratio at the receiver and at the radar end is also shown here. So as the target is moving away, you see the target is actually moving on the radar image. And then as the angles are changing, these are also moving along with that. So this is all good and fine. But now what we would like to do is we also would like to show what happens if the if we were to also observe the communication at the same time. And by the way, as the object was coming closer, you see that it is the signal to noise ratio at the radar end is increasing as well. So let me move on to the next one. Yes, so here there is both the reflector as well as the receiver at the same time. And we are just moving along this line where we keep the distance steady, but we are moving this destination. But now what we are doing is we don't change our initial beamformer. And therefore, as we move away from our original position, the signal to noise ratio actually plummets. And at the same time, just to contrast, look at the constellation here when we were in our original position, which becomes a lot worse if we move away from our original position. Now, let us contrast it with the tracking that is happening. So if we also include the radar's signature to track the object, we will see that the constellation and the signal to noise ratio will remain steady pretty much. And then as the movement is occurring here at this end, we see that SNR is keeping steady because we are repositioning our beamform vector to point at the object that is also receiving the same data. So it is possible in real time to adjust the beamforming vector based on the radar data that we are getting as well. So we can combine them also in hardware. Another feature that may not be very apparent is that when you look at the similar efforts in the literature where people try to use preambles for radar sensing as well as communication, we see that most of those signals are post-processed. That is, people just observe that data, put it in a repository, and once the simulation is, or experimentation is done, they crunch the numbers to come up with the radar images. Whereas this is all done in real time. So this is a truly real-time prototype that allows us to track both objects and communicate with them at the same time. By the way, if we go back and look at the structure here a little more closely, this is a very preliminary implementation with only 4 transmit chains and 2 receive chains. And actually, there's an interesting story behind it, why we didn't want to, we didn't end up going with 4 receive chains either. Very practical issue. We ended up actually burning one of our amplifiers during the test. So we didn't have the time to reorder them and then get them in time to conclude them, which is still in progress. And there was also leakage between the transmit antenna side to the receive antenna side. So we had to increase the separation a little bit. So there's also that. But it is still working in real time, albeit with a resolution of 12 degrees in angle, which can be reduced to half that if we were to go to 4x4 rather than 4x2. So with that, let me just add a couple more concluding remarks here. So we basically focused on OFDM systems, either with a single transceiver chain or a MIMO system with multiple transmit and receive chains. We performed the proof of concept implementation to demonstrate that this is in fact not a pipe dream This is not simulation based. This is all possible in real time, and therefore also a pretty important step forward in terms of what is possible in real life and what we can do. And we are hoping to now move into the implementation of more practical solutions, explore trade-offs on the networking level, what kind of resources we can allocate for communication versus sensing, etc. So all of that can be just studied once we have this system in place, which we now do. Again, we are excited to share all this with you all, and I'm hoping to get a little bit more questions and feedback from you so that we can maybe establish other opportunities in the community. Thank you again for your attention, and happy to answer any questions you may have.